Okay, in this video, we're going to explore the idea of electric potential difference, or just electric potential, if you will. That word potential should be very familiar because we saw that with gravitational potential energy. And this is the exact same thing, except in the electrical world. So gravitational potential energy is based on the fact that objects with mass, if they are placed in a gravitational field, and you move them in either with the field or against the field, you will increase or decrease the amount of potential energy that is available in that field. This is exactly the same thing. Now we're talking about an electric field instead of a gravitational field, but ultimately the idea is still exactly the same. The electrical potential energy is how much energy has been stored or released in the case of the particle's movement, the energy associated with that field. Now, if you put a mass in a gravitational field, you can get gravitational potential energy. So similarly, if you put an electric charge in an electric field, and then you move it either with or against the field, you'll increase or decrease this new kind of potential energy. But this new kind of potential energy it's almost exactly the same as gravitational potential. It's just what it acts on is charge instead of mass, and it is caused by the electric field instead of caused by the gravitational field. But as you've seen, the parallels between gravity and electricity are incredibly close. So for example, the gravitational force between two objects is Gmm over r squared. Now for the electrical force, it would be K Q1 Q2 over r squared. Both of the forces are governed by inverse square relationships with the distance. Both of them are the product of the property that causes this phenomena. So in the case of gravity, it's mass. In the case of electricity or electric force, that is the charge that causes that. Charge causes the electric field. Charge is what allows you to experience the electric field. It's what causes electric force to be exerted on each other. And so the parallels are incredibly close. They're very, very similar. Now there are some differences, and we're going to highlight those differences in this video. But for right now, let's lay out the definition of this new term, electric potential difference. It is like electric potential, gravitational potential energy, except that we're not just going to look at the amount of energy. The work is the amount of energy that it took to move that charge either with or against the field. But what we're going to do that's a little bit different is we're going to divide that by the amount of charge. So this is basically a way of understanding, it's sort of like a proportion. It allows you to proportionally understand the energy. So like, for example, if I raise a pen up by, let's say, 1 meter, there's some energy associated with that. Now, if I lift a car up by 1 meter, obviously that's way, way more energy. Okay, but the potential difference would still be the same. And that is if you take that energy that I raised the pen up and I divide it by the amount of mass, which is a very small amount of mass. So I have a small amount of energy divided by a small amount of mass, I'll get some numerical value. If I take the car's energy, how much energy it increased by raising up by 1 meter, and then I divide it by the mass, I will again get this thing that is proportional. So the amount of energy that 1 kilogram gains by rising up in a gravitational field, that's the same idea we're talking about here. We're talking about how much energy will 1 coulomb of charge receive if it moves through this electric potential. So the definition of electric potential is the work per unit charge, I'm going to write that out as an equation, needed to move a charge from one point to another in an electric field. Remember, for the most part, we don't really care what gravitational energy an object has. We only care how much energy does it have relative to the lowest point that it can go down to. Not to the zero necessarily, but just the lowest point. So for here, I'm over a table, so I would say the table is the zero. That's the zero for H. But if I were to move off to the side of this table so that I could drop this down to the ground, then I would say that would be my new zero. So I don't really care where the actual zero is. It's not really relevant. The only thing that really matters is how much could it change by. I mean, when I drop this pen, it's not going to go through the table. So there's no reason in worrying about the fact that there is potentially more energy that it could gain by going down. It doesn't really make a difference. So the work per unit charge is the definition of electric potential difference. So delta V is the electric potential difference. That's a little bit odd. I realized it's, obviously that's none of those, the letter V is not in any of these. I'm not 100% sure where the origin of that is, but it is a capital V. It's not a script V. It's not an italics V. When you write velocity, that is always a lowercase v, or should always be a lowercase v. And usually it should be written as a script instead of as a regular letter, just to differentiate, because that obviously velocity is a very important property in physics, and we don't want to confuse it with this property, which is also very, very important, the electric potential potential difference. So that's a capital W. Now this is a new property, so we definitely want to make sure that we understand what the units are for this. So in this case, the units for work would be joules, and the units for charge would be coulombs. So when you divide joules by coulombs, those are referred to as volts. Now I'm sure you've heard the term volts. You would see it on batteries, for example, the little round batteries, the AA, AAA, C's and D's. Those are all 1.5 volts. The little square batteries are 9 volts. Car batteries are usually 12 volts. And when you plug something into your wall outlet, that is usually 110 to 120 volts. It varies a little bit depending on how close you are to the power supply. However, essentially what those numbers are telling you, so let's take, for example, the wall outlet. That's 120 volts. What that means is that for every coulomb of charge that passes through that wall outlet, each coulomb will receive 120 joules. That is the meaning of volts. It is how much energy, if you think of a coulomb as kind of like a package, okay, it's a package of charge. It has a certain number of electrons that make up that coulomb, and they can absorb energy. They have the ability to hold on to energy and then also to release energy. So the volts, or the electric potential difference, is how much energy that package will have. If that package has 9 joules, then we would say it's 9 volts. If that one package of 1 coulomb has 120 joules of energy, then we would say that it has an electric potential difference of 120 volts. So I'm going to really emphasize that over and over and over again. The electric potential is all about energy, 100% about energy. Now I do want to show you an alternate version of the equation. There's another equation you can use to solve for the electric potential difference, and it involves using the electric field. So I do want to take a look at that for just a moment. So delta V is equal to work per unit charge, but remember the formula for work is F times D, or 5 times the displacement. It's how much effort you put in multiplied by how far you move that object. Now if we divide that by Q, we get the formula for electric potential difference, and all we've done really is just kind of break it down just a little bit more. Now the reason why I'm breaking it down is because if you just think about this equation, if I multiply F times D, I get W, and I return back to this original version of the equation. But if instead I combine these two guys together, F divided by Q. That should be very familiar from a couple of videos ago, because that is the definition of the electric field strength. So here is an alternate equation. I'm not going to put a box around it because it's not the definition of electric potential difference. It's just an equation that also includes electric potential, but allows me to make the connection between the electric field and the electric potential, right? So the force per unit charge compared to the work per unit charge. So this is really the equation though. Electric potential difference is work divided by Q. Now I am going to rewrite that equation. And part of the reason I'm going to write it like that is because the letter W is a generic term for energy. It represents basically any form of energy. I mean, remember, energy is literally defined as the ability to do work. So while not all energy is used to do work, it represents an ability to do work. So that's kind of generic, right? It's not specific to electric energy. It's just generically the term for energy when you have an object being moved from one place to another. So I'm going to rewrite this equation as W is equal to Q times delta V. Now all I did was solve for W. Okay, I didn't do anything. It's not a new equation. It's exactly the same equation, but I've solved it for W. Now I'm going to rewrite that equation as E for electrical energy is equal to Q times delta V. So this is incredibly important equation, because while this is the definition of electric potential difference, most of the time we will probably use this equation to figure out how much energy did this thing have? How much energy did this electrical system either produce or was it taking in? This is the way that we're going to do it. It's going to be the charge times the change in electric potential. Now that probably doesn't look really familiar to you, so I'm going to make one little substitution. If you remember, I said that the change in electric potential difference is also equal to E times D. So I'm going to make a little substitution right here and say that electric potential energy is equal, now that's really important. This is electric potential difference. This is work per unit charge. But as it is solved for right now, this is just the energy. This is just going to give me some answer in joules. So it's going to be Q times E times D. Okay, now that should be very familiar. Because if you think about gravity, we had this formula for electrical potential energy that said mgh. Okay, these are virtually identical equations. Notice that the first term in there is the property that causes the whole phenomenon in the first place. Everything having to do with electricity, electric field, electric force, electric potential is all based on the charge, and gravitational potential and gravitational energy, gravitational force is all based on mass. If you have mass, you can exhibit and exert a gravitational force. What's the next term in there? The next term here is the electric field strength. What's this term right here? The gravitational field strength. Now that's something, depending on the class, we may not have talked a lot about, but G is essentially tells you how strong gravity is. You know, for example, on the Earth, it's 9.8, but on Mars, it's 3.7 because Mars has weaker gravity, about 1/3 of our gravity. And on the Moon, G is only 1.6 meters per second squared. It is absolutely the same property as this one. It is just applied for gravity. It's a way of measuring the value of gravitational field strength as opposed to electric field strength. D and H, that's the same property. H is a distance. It's just a vertical distance. Those are exactly the same thing. So this is the formula for gravitational potential energy. This is the formula for electrical potential energy. Now, you don't have to use E times D. In fact, we will probably not use that very often. I would say that'll be pretty uncommon that we'll use that. We will mostly just simply use this. So if I move 1 coulomb of charge through an electric potential difference of, let's say, 12 volts, then that means that I will have expended 12 joules worth of energy. So that's exactly the same thing we would have done with the electric potential energy. So very, very similar to each other. One thing I just want to point out is, realize that this is delta V. There is an equivalent thing. There is something called gravitational potential. Not gravitational potential energy, gravitational potential. There is a delta V for that. Now, we didn't talk about it because it's like a kind of an advanced aspect of gravitational energy, but G times H is what's going to determine how much energy this mass is able to get, just like E times D is going to determine how much energy this charge is able to get. How far it moves and how strong the field is are going to determine how much energy that particle is either going to gain or how much energy that particle can give up if it was, for example, to be converted into some other kind of energy. And we'll look at that in just a moment. So let's continue forward with this. What I want to look at, besides the equations, is there is one difference between gravity and electric field, and that is that there is only one kind of mass. All masses go with the field. They always move in the direction of the field. The problem is with electric charge, there's two kinds of charges. There's both a positive and a negative, and of course they behave in completely opposite manners. So what I'm going to do down here is to draw an electric field, a strong electric field. It's going to be uniform, so I'm going to have the field pointing to the right. I'm going to make the lines parallel to each other. The lines being parallel indicates that the field is uniform, that the field is not changing. Sorry, here we go. It'd probably help if you could see what I'm doing. So in these lines, I'm going to draw a couple of things. I'm going to place one positive charge, and I am going to place one negative charge. Okay, let's talk about what happens to these things. So first of all, the positive charge is going to feel a force in the direction of the electric field. Remember, this is E, the electric field, not energy, right? This is something that could be a little bit of a point of confusion because we are using, if you notice, the letter E was in there twice. Once as energy without the vector symbol over it, and once for electric field with the vector symbol over it. That's why I'm going to really emphasize putting that symbol over the electric field strength, because it could be confusing, especially when you think about how closely related it is to electrical energy. So really important to put the little vector sign over the top to just indicate this is the electric field, not the energy that we're talking about. Now, obviously, negative charges always do the exact opposite. So if these two are identical charges, he will feel the exact same force, except that that force will point in the opposite direction, right? So that is something that is not something you would see with gravity. Gravity always goes with the field. So if I place a little mass here, it's going to go with the field. If I place a little mass here, it's going to go with the field. But these guys are not going to. Okay, now the question, and this is where it gets a little bit confusing, is normally what we would say is that if I took this positive charge and I pulled it against the field, if I did work against the field, just think about the sound of what I'm saying. The work against the electric field, that's exactly the definition of gravitational potential energy, is the work that you do against gravity. So if I take this positive charge and I move it in this direction, I will be increasing the electrical potential energy. So I'm going to draw a little dotted line with an arrow. And what essentially we're doing here is we are gaining electrical energy. Now, what would happen if I just let this particle go? Well, the particle would begin to speed up because it feels a force. It's going to begin to accelerate, and it's going to begin to move in this direction. And instead of gaining electrical energy, it's going to lose electrical energy. And what's going to happen is it's going to gain kinetic energy. Particle is going to begin to pick up speed and travel faster and faster. But to complicate things, of course, the negative charge always has to do the exact opposite thing. So if you were to release this particle, it would not move to the right because negative charges don't move with the field. They always move against the field because their force is always opposing that direction. So if we were to move in this direction and we just let the particle go, that's the direction it's going to want to go. That's really important to understand. The particle, if I let go of a negative particle here, it will naturally start going against the field. It always goes against the electric field. So in this case, we would be gaining kinetic energy. But if I take this charge and I pull it with the field, which it doesn't want to do, it's going to fight me when I try to do that, then I will find that I am going to be increasing, or I will gain electrical potential energy. Okay, so it's not a big deal. It's like a minor thing, but it is important to understand that when you go against the field with gravity or with a charge, you increase the potential energy, and if you let it go with the field, it's going to increase the kinetic energy. It's going to decrease the amount of electrical or the gravitational potential energy. But this little extra twist that the negative charges always do the exact opposite. So in a situation where a positive charge would gain electrical energy, this guy would be losing electrical energy as he does that. Now that's the reason why this little qualifier about only in the direction of the electric field. Now it's either in the direction of the electric field or in the exact opposite of the direction. But if, for example, I were to move sideways, well, that wouldn't do anything. And just to give you an analogy, I have this pen above the table, but if I move it away from me or I move it closer to me, I'm not changing the gravitational potential energy because it's not going with or against the field. If I go against the field, I increase EP. If I go with the field, I'm decreasing the amount of potential energy. But when I go sideways to the field, I don't get anything. It's not to say that there's no energy involved, but there's no gravitational energy involved. And that is the same thing in the case of the electric field. So let me draw these two just so that we can, I really feel like it's helpful to think about how gravity worked. As a way, because that's more familiar to you. We've really studied it for quite a long time at this point. I feel like it'll make more sense. I'm going to start on the gravity side. Say we had a roller coaster and the roller coaster went down, went through a loop, and then eventually came down to here. What determines how much energy that this car has is based on its mass. It's based on gravity, which is, of course, not something that we can really change. And it's based on the height. When the little roller coaster car comes down here, and let's assume that there is no friction acting on the car, the amount of energy that this car is going to have is determined by how high it started from. So it's going to have a certain amount of kinetic energy, but it wouldn't have mattered if I went down a very gentle slope like this, or I went down a very steep slope. I'm going to have the same speed no matter what, because all of that energy for the kinetic energy is coming originally from the gravitational potential energy. So the fact that the car moves sideways, the car doesn't gain any energy when it moves sideways. So during this portion, the car is gaining kinetic energy. But as the car moves horizontally right here, nothing's really happening to the energy. Everything's basically staying the same. Same kinetic energy, same gravitational energy. It's only when we move vertically that we make this trade, this swap of gravitational potential energy for kinetic energy, I should say. Okay, so the side-to-side motion is not relevant. It's only the vertical motion that really matters because that's the direction of the gravitational field. The gravitational field points directly down towards the center of the Earth. So for the electric field, if you were to imagine an electric field, let's point it in a different direction. Let's go this way. So I have a nice uniform field, just like I would have a nice uniform gravitational field if I get on a roller coaster. Gravity is pretty much the same everywhere. And if I were to start with something up here at point A and I was going to go down to point B, it really wouldn't make a difference how weird or loopy or how strange the path is. The only thing that matters is how far did we move in this direction? how far did you move in the direction of the field or in the opposite of the direction of the field? And that's where we were talking about the D right here. That D, remember, is the same thing as the H right here. Over here, the H was vertical because that's the direction of gravity. Over here, I chose to make the field go to the right. I could make it go any direction that I want to. It's much easier to manipulate an electric field than it is to manipulate a gravitational field. But the only gain in energy, electrical energy, comes when the thing is moving either this way or moving this way. So to give you an example, right here, there's a little portion where this line is nearly perpendicular to the electric field line. Nothing was gained there. There was no change in the electric potential difference during this portion of it. Now, during this portion where it was moving parallel to the field, yes, definitely we were gaining some, in this case, either gaining electrical energy or we were gaining kinetic energy as the object moved. Just depends on what kind of charge we moved from A to B. We would get a different answer if we move a positive charge than a negative charge, even though the number would be the same. Whether we were gaining electrical energy or whether we were losing electrical energy, that would be determined by whether we had a positive or a negative charge moving from this. Now, let's take a look at a few example problems just so we can make it a little bit more concrete in your mind. How do you use this electric potential difference? So let's move this out of the way. And let me give you, I'll try to give you 3 kind of basic problems just so you get a little bit of variety of each of the different things. So first, let's not do anything fancy. Let's just calculate the electric potential difference between point A and point B. In this problem, 3.6 millijoules were required to move a 4.7 microcoulomb charge, millijoule and microcoulomb charge from point A to point B. So first thing I'm going to do is I'm going to write down the properties that I was given. So this is 3.6, but one thing really important is we can't plug in milli, we can't plug in micro into these equations. We need to take these back to their base units. So this needs to be in joules and this needs to be in coulombs. So I'm just going to take the milli. Milli means 10 to the minus 3. That guy is now converted. I'm going to do the same thing for the charge. The charge is 4.7 times 10 to the minus 6 because that little symbol micro means 10 to the minus 6 coulombs. And what I'm looking for is delta V. Okay, so in this case, pretty simple equation. So it's W divided by Q. We don't need to do any algebra. It's 3.6 times 10 to the minus 3 divided by 4.7 times 10 to the minus 6. Bring out the calculator. There, let's move this way. Okay, so it's going to be 3.6 second function EE to the minus 3 divided by 4.7 second function EE to the minus 6 is equal to, and that appears to give, here, let's put this into regular notation. That appears to give 766 volts. So delta V is equal to 766 volts. Now, one thing that's really, I guess, kind of interesting about this new property, electric potential difference, is that the property and the units use the same letter. And that is more than likely the first time that has ever happened for you in a physics class. You just take a quick run through some of the properties we learned. Force, but that's in newtons. Energy E, but that's in joules for the units. Velocity, meters per second. Distance is in meters. Almost always the units are a totally different letter than the property. There's a few cases where they're the same, and this is the first one that we've really run into. The units for the electric potential difference are called volts. Now there's another kind of additional thing, and that is that electric potential difference, and you definitely should write this down. Electric potential, we'll just leave it at that. That is the same thing as voltage. That's I don't know, I find it kind of a peculiar thing, this idea that if you took the units and you added the letters AGE to the end of it, we would use it like that was the name of the property. So most electricians, they aren't that familiar with the idea of electric potential difference, but they know what voltage means. But it's actually the same thing. There's no difference between the two. The voltage is referring to the electric potential difference. I would say the word voltage is kind of like a nickname. Like, for example, people who have the name William might go by Will or even Billy. Those are nicknames. It's not the proper name for the thing, but it's like a kind of a casual nickname for the property. So you may hear me going back and forth between saying electric potential difference and voltage, but they're exactly the same thing. There are a couple other places where that happens. When you talk about land area, they will often talk about acreage. So the acreage is essentially how much land area that you have or that you're talking about. Also, when they measure like ships, oftentimes they will talk about the tonnage. So instead of saying what's the weight of the ship, they'll say what's the ship's tonnage. It's the same thing though. It's exactly the same thing. They've added the letters AGE to the end of the units, and now that unit becomes the name of the property. So in this video, I'm going to keep referring to this as electric potential, but you will definitely see as I get to electricity that I will pretty much stop saying electric potential, and almost exclusively I'll be saying the word voltage. It's just a little easier to say in the first place. So that's the basic idea of electric potential. Now let's take a look at the idea of calculating how much energy was either gained or lost by an object as a result of passing through a potential, an electric potential. So the question is, how much energy will be gained when an electron travels through a 120 volt electric potential? So in this case, it may seem like we didn't have very much information. We certainly have delta V, that is 120 volts. Okay, now in order for me to get the electrical energy, I would need to know what Q is. But because I was told that it was an electron, I know what that is. That is given to you all the time. You'll have that whenever you need to use it. You will be given the charge for an electron. That is the fundamental charge. That is 1.6 times 10 to the minus 19. And that will always be the same. Now, it could be a proton or electron. It will always be the same charge. The only difference being that obviously the electron will be negative and the proton will be positive. So what we're looking for here in this case is I could either write the letter W or I could write EE. That's your choice. It doesn't really make a difference to me. It would be very clear to me if you wrote W equals Q times delta V, I would understand what you were talking about. So in this case, delta V is equal to the electrical energy divided by Q. So therefore, if I were to solve for EE, EE would be equal to Q times delta V. Remember, super important equation that we're going to be using a lot in this chapter. So in this case, we can go ahead and plug things in. 1.6 times 10 to the minus 19. And then I'm going to multiply that by 120. Bring the calculator in and we'll go ahead and make the calculation. So 1.6 second function EE to the minus 19 times 120 equals, and in this case, we would get 1.92 times 10 to the minus 17. So very, very small amount of energy. Obviously an electron, not a very big guy to be moving around. So not surprising that that is such a small amount of energy. Okay, now here's the question. What are we going to do with this energy? Well, most of the time what we're going to do with this energy is, just like with gravitational potential energy, we're going to turn that energy into kinetic energy. So in this follow-up question, this is really kind of like a part B to this question, so let me leave both questions up. The question is, how fast will the electron be traveling after it passes through this 120 volt electric potential? Just like when I drop this pen, I know that the gravitational potential energy will turn into kinetic energy as I allow it to fall, and I can use that relationship to figure out how fast a pen would be moving, or really any object, if I drop it, how fast it will be moving. So in this particular case, here's what we're doing. We're saying EE must be equal to EK. So that electrical potential energy, the 1.92 times 10 to the minus 17 joules, that will all be turned into kinetic energy. So I'm going to go ahead and write the equation. I want you to see visually the equation. The EE side is going to be Q delta V. Remember, Q delta V is like the MGH of the electrical world. Just like MGH is the formula for electrical or for gravitational potential energy, Q times delta V is the formula for electrical energy. And we're going to set that equal to 1/2 mv squared. Okay, now there's no cancellation or anything like that. However, one thing I will point out is I've actually already calculated Q delta V. I already did it in the previous problem. So I really don't need to recalculate that, and I'm not going to do that. Instead, what I'm going to do is we're just going to plug it in. So 1.92 times 10 to the minus 17 is equal to 1/2, and I'm going to tell you the mass of the electron. You would never be expected to memorize the mass of an electron. That's kind of a pointless thing to memorize. But it is 9.11 times 10 to the minus 31st. That is mind-bogglingly small number. That is really hard to put into perspective. If I move this decimal place 31 places to the left That'll give you an idea of just how small of a number this is. Electrons are teeny tiny little guys. So even though this is a very small amount of energy, electrons are so small that you're going to find that this really is a huge amount of energy. So let's do this. First of all, I'm going to get everything over to the other side. So all I'm going to do, you can just kind of follow along with the algebra that I'm doing. I'm not going to write it on the paper, but I'll show you what I'm doing. It's 1.92 second function e to the minus 17. Okay, first of all, I need to get rid of the 1/2. I'm going to multiply by 2. That's going to move it over to the other side. It's equal to this. Then I need to divide by 9.11 second function e to the minus 31. Gigantic number. Okay, now remember that's not the final answer, right? Because this is still v squared. But I am going to go ahead and write that number down. That number is 4.2 times 10 to the 13th. Okay, now all I need to do is take the square root of that number. So I'll set second function square root, second function answer. That'll bring back my previous answer. And I end up with an answer that says, this says that v is equal to 6.5 times 10 to the 6 meters per second. Okay, and I really want to put into perspective this. You're talking about sending an electron through the electric potential difference that's everywhere in your house. Every wall outlet in your house has about 120 volt electric potential difference. So if you were allowed an electron to experience that 120 volt potential difference, you would end up with a speed of 6.5 million